Let's take a look at number one. So an offshore oil well is located at W, point right here, 5 miles from the closest point on shore, which is A, right here. Oil is to be piped from W to B, here all the way to here, by piping it underwater from W to P, and then over land from P to B. So this is underwater, this is above water, or above ground. If the cost of the pipe underwater is $100,000 per mile, and the cost over land is $75,000 per mile, where should point P be located to minimize the cost of the pipe? So we're trying to figure out where this point should go. We kind of have some leeway. We could go straight to A and then go above land all the way to B. Or we can go underwater the whole way, but we're trying to find the most cost-effective approach, which is probably somewhere in between. So we want to figure out where should this be to be most cost-effective, to be the cheapest. So right there, it's kind of further down the line, but you can kind of see it right here. We're trying to minimize the cost. All right, so we're going to end up having to write an equation for the cost. Some of the key things here: underwater piping is $100,000 per mile. Over land, $75,000 per mile, and we have some of the stuff labeled here. So let's go ahead and kind of jump to the equation. We're not going to write it out completely yet. A lot of times it might help you just kind of think the problem through. Before you start putting it into a serious math equation, just kind of put it in words. We're trying to minimize the cost, right? So we have to write an equation for cost. Well, what two costs are we taking into account here? Underwater and over land, right? So we need to figure out the cost underwater plus the cost over land. So that's like our basic equation. Now we're going to have to kind of throw some variables in there and make it look a little bit more mathematical. But that's the basic idea. We need to write an equation that looks like this, or that kind of fills this in, and then we can kind of take those, the rest of those steps. So right now we have no variables. We know this is 5 miles, this is 8 miles. We're trying to figure out where this point P should be. So I'm going to go ahead and label this little segment from A to P. We're going to make that X. Because that's kind of what we're trying to figure out. How far away from A should that be? Well, if this is X, and this distance from A to B is 8, what's the distance from P to B? 8 minus X, right? Good old geometry coming back. All right, we're trying to figure out what those are. If they both add up to 8, and this is X, this has to be 8 minus X. So that, 8 minus X, that's going to be our distance over land. Right, 8 minus X is our distance over land. This right here is going to be our distance underwater, but we need a variable. We need to write that using a variable. Well, we've got this triangle going on here. It's a right triangle, so we can use Pythagorean's theorem. Right? If this side, let's just say that's C for a second. I know we want everything in terms of one variable, but we'll write this in terms of X in just a second. If that's C, we know by Pythagorean's theorem that X squared plus 5 squared has to equal C squared. So C, we take the square root of both sides, that's just going to be the square root of X squared plus 25. Right, so that's our distance underwater, the square root of X squared plus 25. Right, so now we've got everything in terms of X. We need our equation to be in terms of one variable only. Well, now let's kind of put the pieces together. The cost underwater, it told us it's $100,000 per mile. Well, to find out the actual cost, we have to know the number of miles. Well, that is right here. Right? That's the number of miles. So our cost is going to be 100,000 times the square root of X squared plus 25. plus cost over land, that's $75,000 per mile, so we have to multiply by that by the number of miles. That's right here. That 8 minus x is the distance that it's going to be above ground. All right, so now we have our equation C in terms of just one variable, x. Our next step, right, we've done up to step 4 at this point. We want to find the critical values. So we want to figure out when the derivative is 0 or does not exist. So we're going to end up taking the derivative. Before I do that, I'm going to go ahead and distribute this so I don't have to use product rule over here or anything like that. So C is 100,000 times square root of x squared plus 25 plus 75,000 times 8, that's 600,000, minus 75,000x. And so now we're going to go ahead and take the derivative of that equation. Well, for this first one, that 100,000, that constant's going to stay out in front. We're going to need the chain rule to take the derivative of this. This is like x squared plus 25 to the 1/2. So bring that 1/2 out in front times the 100,000, that gives us 50,000 times x squared plus 25 to the negative 1/2. But then we have to multiply by the derivative of the inside, which is 2x. Next term is just a constant, so what's the derivative of a constant? 0. All right? Minus derivative of 75,000x is just going to be 75,000. So we can kind of clean up that first part here. The 2x times the 50,000, we get 100,000 times x, all over the square root of x squared plus 25 minus 75,000. We're trying to figure out when this is equal to 0. Now we could solve this algebraically. It's a lot of steps to take care of. Add the 75,000, multiply by the square root, go on from there. But another option for this one, we can just use our calculator. We want to figure out when this is equal to 0. Let's go ahead and graph it. So I'm going to put this in for my y equals. So I have 100,000 divided by square root of x squared plus 25. Oh, thanks guys. Close. So I want to go back up here, x in. And so 100,000x divided by square root of x squared plus 25 minus 75,000. All right. Before I graph this, let's think back to this problem. What's the smallest x could be? Remember I talked about a couple options. We could just go underwater from W straight to A, and then above ground the whole time. Probably not the most cost effective, but that would be an option, right? So if we did that, x would be 0. Or we could go from W straight to B, where then x would be like 8. We go that whole distance. So those are our endpoints, 0 and 8, right? Our critical values would have to be between 0 and 8 somewhere. So with that in mind, when I go to graph this, I know I'm going to be okay as long as I'm going from 0 to 8. So I'm just going to go ahead and change my window. Our x-min, I'm going to do 0, x-max is 8. So we end up with one critical value right here. So we can figure that out. We do second trace. We want to calculate the 0. Oops. All right, so we're going to calculate the 0. Left bound, this was going up here. So I know 5 is going to be to the left of that. and 6 is going to be to the right. Enter one more time. We get 5.669 approximately. Now, I'm going to show you something, because a lot of times we want to use this whole decimal, not just a rounded decimal. So what I want you to do is go and hit second mode, which is just quit. So second, quit. And then if you hit the stow button, S-T-O, right above the on, we're going to stow it, whoops, for X. All right? So now, whenever I use X until I change it, like in this window, it's going to substitute that number in the place of X. So like if I did 2X, it's going to be double that. Right, so like for the rest of this problem, if I have to plug that in somewhere, it's going to be nice. I can use the whole decimal instead of just that approximation. All right, so yeah, 5.669 is our value. We want to test that and make sure that's going to be our minimum. So we're going to go ahead and test our endpoints. We want to figure out what's the cost if X is 0. What's the cost if we use 5.669? And what's the cost if we use 8? Alright, so we want to take those values, our endpoints and the critical value, and plug them back into the original equation. Alright, so we're plugging those back into the original equation. So let's go back. I'm going to go ahead and change my y equals. I'm going to put in our original equation now. Too many zeros there. Alright, so we have 100,000 times the square root of x squared plus 25 plus 600,000 minus 75,000 x. And now if I go to my table, second graph, I can put in my values, which are already in there. But 0, if you wanted to, you could put in x. And that shouldn't mean the same thing, but it gives me the whole decimal. All right, so we have those 3 values there. So if we go straight underwater to A and then above ground the rest of the way, it's going to be like $1.1 million. Not our most cost-effective approach. If we go to that critical value, it's going to be $930,719. And if we go straight underwater the whole time, $943,398. So it does turn out that this is going to give us our minimum cost. So I'm going to go back and make sure that we're answering the question that's asked. It asks us, where should point P be located to minimize the cost? Well, X was 5.669, so that means P should be 5.669 miles from A. So that should be our final answer. That P should be 5.669 miles from point A.